The next speaker of this session is Jose de Ramon, and he's from University of Waterloo and University of Patras. He's going to talk about effective notions of causality in detector models. And Jose, you're going to have 12 minutes, and 2 minutes before I'll give you a warning. And whenever you're ready, the floor is yours.
Okay, perfect. Well, thank you very much for letting me share my work with you all today. Today I'm going to talk about effective notions of causality in particle detector models. This is a working collaboration with Maria Papageorgiou and Eduardo Martin Martinez, both from the University of the Waterloo, and Maria is also at the University of Patras. As we've seen many times during this conference, detector models provide us with a tool to discuss many aspects of quantum field theory in both flat and curved spacetimes. Perhaps the most interesting example, or the most, say, foundational example, is about the local measurements that they enable us to perform local measurements of quantum fields. They also can be used to clarify the meaning of several quantum field theoretical quantities, such as the en route temperature and associated phenomena. They also can be used to probe some aspects that are related to entanglement in quantum field theory, such as entanglement harvesting. And most importantly, for this talk, they provide a natural ground for discussing the transmission and processing of information, both quantum and classical, by means of quantum fields. So the question is, why is it relevant to consider a relativistic quantum field theory as a medium for the transmission of information? The reason is that quantum fields, concretely relativistic quantum fields, naturally obey relativistic causality, which basically says that information cannot travel faster than the speed of light, which is the maximum speed of propagation. In this sense, if you have, say, an array of detectors that are all interacting with the same quantum field and they're space-like separated, then their local statistics should be independent because they cannot send signals to each other. In this work, as well as in our previous work in impossible measurements, I'm going to use the general picture for general linear particle detector models. The general picture of a detector is given by an auxiliary quantum system that becomes correlated with the field through a local interaction. You can think about this object as a term that the one adds to the action in such a way that the field and our system of interest interact in some way in spacetime, or as a Hamiltonian density in the interaction picture. Examples include, for instance, the en route with model, with typically a spacetime smearing, quantum particles such as a particle in a box, a harmonic oscillator, etc., that in which the spatial degrees of freedom have a quantum mechanical character, as developed by Andrew and Wald in one of their seminal papers. And more recently, to actually use quantum field theoretical detectors as probes for the quantum field of interest. What I want to discuss here has to do first with the causality and signaling. And I want to clarify that overall, causality and signaling are conceptually difficult notions, even at the classical level. In this talk and in this work, the way we discuss signaling is the following. Given two independent parties, say Alice and Bob, we say that Alice can send signals to B, to Bob, if the local statistics of Bob do not depend on the free parameters associated with whatever A is doing, say an interaction with the field, or say a concrete preparation of an initial state. This is the take that is taken in many ambits in physics nowadays to discuss causality and signaling, such as the process matrix formalism. In our case, for an arrangement of detectors that interact simultaneously, or should I say that they interact in an array of different interaction regions with the field, we say that a detector can signal, a detector A can signal a detector B if the local statistics of B depend on the coupling constant of detector A, that is lambda A. The intuition is that if the statistics of B do not depend on whether the interaction took place or not, there cannot be any signaling, because Bob cannot distinguish whether the interaction of A happened or not. So at least we would know that the interaction is, or the signaling is not through the quantum field. How does signaling relate in this sense with relativistic causality? Well, this is something that we discuss in this paper that Doreen mentioned. The microcausality action for the field is that the amplitude of the field when evaluated in space-like separated point vanishes, implies that pairs of detector interacting with the field in strict space-like separation cannot signal each other. Of course, what we also saw there in that paper that in arrangements that have more than two detectors, superluminal signaling can happen because of the self-interaction of the middle detector. And this is something that we related with the so-called Sorkin's impossible measurements. We also saw in that paper that at the lowest non-trivial order in perturbation theory, these three detector scenarios are not relevant. And because the total statistics only depends on pairwise interactions. And if you are more like a higher energy physics oriented person, you can think about the vertices, for instance, and a linear interaction. So what happens, and this is the purpose of this talk, when detectors are not strictly localized in spacetime? For instance, consider atomic models. The localization of the atom is not going to be given by a strictly confined sharp region in spacetime, but it's going to be given by the orbitals of the atom that are going to be objects that are going to be exponentially localized in space, but not strictly compactly supported in space. Also, in materials where one considers some non-relativistic quantum field theory, this field theoretical description is not available at all resolutions or at all energies, if you want to think about it that way. And more generally, it is convenient for calculations to consider space-time smearings that are not strictly localized in space-time. So, but then what about causality in this kind of situation? Because if the detectors are interacting everywhere with the field, there is no notion that they cannot, that they're in space-like separation, and the macrocausality condition for the field is not going to preclude the any kind of signal in between them. However, physically, we should have some sort of effective notion of space-like separation when the relevant quantities that determine the detectors are mostly localized around some region of spacetime. So this motivated us to introduce a quantitative notion of signaling. Remember that we are defining signaling as the ability of a detector B to infer the value of the coupling constant of another detector A that is somewhere else in spacetime. Therefore, we would like a notion that quantitatively encodes this property. We argue that actually quantum metrology has the answer, and that the quantum Fisher information provides with a nice figure of merit to encode this notion of signaling. Indeed, the quantum Fisher information is given a parametric family of density matrices on a system, something that bounds the variance of the optimal parameter estimation when performing quantum measurements. Therefore, this provides with a good notion of signaling in the spirit of the definition. And to give you some intuition, we say that a low Fisher information for the reduced density matrix of B after the interaction with respect to the coupling constant of the other detector implies low signaling. One can calculate in perturbation theory an expression for the Fisher information described above, which will be proportional at the lowest non-trivial order to the variance of the self-adjoint operator, which is given basically by this convolution with the retarded propagator, which is an object, by the way, that doesn't depend on the state of the field, and that lives in the future Lycon, in the sense that if x and y in this expression are space-like separated, or x lays on the past of y, then this expression vanishes. So for for detectors that are exponentially localized in some sense, we were able to calculate the expression in some situations. In particular, it is easy to evaluate and to bound this expression in situations in flat spacetime. For unruly with detectors, and more concretely, co-moving detectors, there is the velocity of one of the detectors is not very high with respect to the other. And for spacetime smearings that are exponentially localized in spacetime, there is basically, we say that the function times an exponential is integrable, which means that this decays faster than light in some direction. In the case of unruly with detectors, we could bound the expression by an exponential. In the case where C, there is the special space-time separation between the detectors, is either past or spaceless. Indeed, if you look at the expression, it should be, there's a type, we should say positive. Then this expression, we see that is exponentially decreasing when the time difference of the detectors goes to infinity. Just to exemplify a little bit what this effective light cone is going to look like, I plot the expression, the exact expression in the case of Gaussians. In this plot, we see the time difference between the detectors and against the radius. So this is a space-time diagram. 0, 0 represents the position of detector B, and the rest of the points represent the signaling if the detector A was placed there. I'm gonna pass the issue of whether detectors become transparent given the difference of frequencies and resonant phenomena. I'm going to pass directly to the conclusions and outlook. We have motivated the introduction of a quantitative measure of signaling. Our signaling estimator can be used to extend operationally the notion of relativistic causality to situations where effective models do not allow for strict localization. Although we have shown here flat and rooted with spacetime calculations, the formalism extends to more general detectors. That was the initial motivation, and also to curve spacetimes. The exponential localization applies in many situations of interest, such as particles in potentials. Finally, some outlook. Non-relativistic fields exhibit supernominal signaling, and it is expected that the results can be applied by rewriting local interactions with non-relativistic quantum field theories as the localized interactions with causal quantum field theories that have a nice notion of light cone. And with that, I would like to thank the audience, and if you have any questions.
Thank you so much, Jose, for the nice talk. I'd like to know if there is any quick question. Well, if not, we can move for the next speaker. But before, let's thank Jose